30-1, so I'm just going to do a video response to make the key for this assignment here, this worksheet. Might as well just make a video one because I'm just going to make the key. So while I make the key, I'll just talk about what I'm doing. If you don't want this, I'll just post the PDF answers online. You can just double check yourself. You can just come back to this video if you want to see how I did a certain question or why I did a certain question the way I did. Okay. So what we have here is we have the population of a particular insect. It decreases by half each night that the temperature goes down by 0. So that's giving me a good hint about what the C value of my equation is going to be. It looks like the C value is going to be a half. And so for most of these equations as I go down here, my equation that I'm going to be using is going to be A times C to the power of T over P, where P is my period. So I'm going to write an exponential equation for the population that's remaining. So you can see here my Y value is P. So my equation is not going to be Y is equal to, it's actually going to be P is equal to. My initial amount, they don't give me any initial amount. That's what the A stands for. You remember that from our lessons. That's going to be where it starts. This is going to be, I could just call that the base. And this P stands for the period. Okay. Since we're talking about each freezing night, my period is probably just going to be 1. And they're just going to say N instead of T here. So let's just say I start off with 1 for 100%. And then my base value is a half, and then I'm going to raise it to the power of n. So that's what my equation looks like. And now I can graph that. What I know that this graph here is decreasing. It's a decay function. So it means it's going downward. So the highest that this graph will be is at 1. And then it's going to go down to a half after 1 freezing night. So 1 freezing night later, I'm at a half. And then I'll get rid of the dot that I had there. And then about half of that half, after 2 freezing nights, I'll be here. Then half of that half will be 3 freezing nights, and half of that one would be 4, and then half of that would be 5. So this is what my graph looks like here. Now it's going to have an asymptote there, and that's what the equation looks like when you graph it. Now it asks me for what percentage remains after what percentage remains after 5 freezing nights. So they're asking me when my N value is equal to 5, what is my P? Okay. In percentage. Okay, so my equation here, I'm just going to put in what I have. So P is equal to 1 times a half raised to the power of 5. And then I'm going to punch that into my calculator. My calculator on my other screen here. I get 0.03125, but I want this to the nearest 100th percent. So I get times this by 100%, and I'm going to get 3.13%. So 100th is 2 decimal places. So there we go. Okay, so in the next one here, we are going to invest $1 in a compound interest. So I'm going to assume that this percentage, if they don't give it to us, per year, and this is compounded annually. So that means my C value in my equation that I have up at the top there is going to be 100% plus, because it's an increasing amount, just the regular percentage. So I'm not going to change this percentage. You're going to see later on when we have compounded quarterly and compounded semi-annually, you're going to have to change this number. But what I know is that my C value is not going to change considerably, so it's going to be 1.045. So we have an equation for V, that's my investment, where I invested $1, and then I have a growth function, not going to be growing very fast, and then I'm going to have the growth base here to the power of T over P. Because it's compounded annually, my P value is 1. So I could write divide by 1, but there's really no point to write divide by 1. Okay, so that's what my graph looks like, or sorry, my equation looks like. So what I'm going to do now is I'm going to graph this. So I'm going to put this over here. Okay, and then I'm going to 1 times 1.045 to the power of x. Okay, I'm going to zoom standard. So this is my graph looks like. You can see it's slowly going up there, but there's a lot of empty space here that we don't need. So we don't have an x min. We'll put that as 0, and then we don't have a y min. We'll put that as 0 as well. because there's no point for those values. There's no negative time, and there's no negative value. So it's starting down here at 1, and it's going upwards. So I'm just going to change my window, my X max here, to be a little bit more. So let's change it to about 50. Let's see what that looks like. That looks pretty good. Okay. Then I'm going to change my scale at the bottom here to be, I don't know, 5s instead. So it was 5, 10, 15, 20, 25, 30. And let's see what that graph. So this looks a little bit better on the bottom. So this looks pretty good. Now I want some of these points so I can plot them. So I can graph it out. So I can go to my table. Now if I go to my table, I'm going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what I can do here is I can set my table. So I can go second window. And rather than going up by 1s here, this delta table here, I could change that to like 10, or I could change it to 5s. So I can get some better points. If I do that, then I go back to my table. You can see that now it's going up by different values, or you can see that I have a bad starting point here. So let's start the table at 0 instead, and then go back to our table. So it was 0, 5, 10, 15, 20. Okay, so now I know some good points. So what I'm going to do now is I'm going to plot those points. I'm going to start here at $1. So this is dollars. It's my scale. $1. I'm going to start there. There's 2, 5, 10, 15, 20, 25, 30, 35, 40, 45. Yeah, so let's go up by 5s here. 5, 10, 15, 20, etc. Okay. So 5, I should be at 1.24, so about 1 1/4. So right about there. At 10, I'm at 1.56, so right about there. 15, I'm almost at 2, so right about there. 20, I'm at 2.4. 25, I'm at 3. 20, so I'm just going to go up and just plug in my values here. Don't need me talking all this time, do we? 4.6 now. So let's see. Yeah, 4.6 right about there. 5.8 somewhere right there. 7.2. Oh, and then 9. All right, so there's my graph. Cool, looking pretty good. What's the value of the investment after 15 years? So question C, they're just looking for value when n is, or sorry, t in this case, t is equal to 15. Okay, so I'm just going to plug it into my equation. V is equal to $1 times 1.045 raised to the power of 15. I'm going to go over to my calculator here and just punch that in. So 15, you can see, oh, I had that number before actually. So $1.94, so 93.5. Okay. Not a very good investment. You only invested $1 anyway. Use the graph to determine the time needed to reach $3 exactly. Okay, so what I'm going to do for that is going to go back to my graph here. So what I'm going to see is I'm going to graph here. I want to know what $3 exactly. So right about here somewhere, right? So I'm going to go to my y is equal to. I'm going to put 3 in here, and you're going to see I'm going to create a line at 3. So y2 has a 3 in it. And then I'm going to look at the calculation here. I'm going to find the intersection point between the two. So when my y value is 3, which is my value, it takes about 24.96, so about 25. Let's just say that. This is to the nearest year. So after just looking at the graph here, it's about 25 years. So if you wanted to, you could draw that line on here. So that's the $3 line. That read down 25 years. Okay. All right, so we're going to continue on here. Let's see what else we have. We want to write an exponential function that models the amount. So m remaining after D days here, and I've got a few things up here. So we have a half-life at 8 days. Just scroll up here. So my half-life is 8 days, so I would say that my period is 8. Okay? This means that after 8 days, the original amount is half as much as it was before, so that's what we know about that. Suppose we have an initial amount, so this is going to be my A value. It's 250. You can put units there if you want. So my equation is going to be 250. And because it's a half-life, my C is going to be half then, raised to the power of D over 8. So there's what my equation would look like. Now I can graph this, and I can state the domain and range and stuff as well for this one, right? And what the m-intercept of the graph is. So actually, I'd probably do most of that before we start. It's a nice decay graph, so that's good. So what I know about the m-intercept is where does the graph start? So that's when d is equal to 0. So if I put that into my equation up here, I'll realize that my m-intercept is going to be 0, 250. So I know that's where it's going to start. My domain is going to be just the d values down here. So that's going to be d such that I'm going to start at 0. I'm going to run to something. I don't know, it probably goes on forever. So let's just say everything that has to be greater than or equal to 0. And d, er. Right? Then my range is going to be starting at 0, starting at the max value because it's a decay graph, because it's decaying the half, the C value is a half. So my range is going to be m such that, and it's going to go down to 0, and the highest it'll go is 250. So I know that it can get to 250 because that's where it starts, but it's not actually going to get to 0, theoretically. It probably will get to 0 because it's an actual thing. And the horizontal asymptote. Now I put this into the right form here, so it's going to be horizontal asymptote is m is equal to 0. So it's like y is equal to 0 because it's a horizontal line. So you say y is equal to, but there's no y value, so it's actually m in this situation. So we have the domain, the range, the equation, and the asymptote. Yeah, so we got all 4 pieces. Okay. So what I can do now is I can just create a scale here. 1, 2, 3, 4, 5, 6. That doesn't really matter. So I could say that this is 250. Okay. And then down here, this is going to be 125. That's just half that value and then half that value. So I just know it's going to look very similar to the graph of the very first one, but my scale is just going to be a bit different. And then here is I'm going to put down, let's say I'm going to put every 2 boxes, I'm going to have 8 days. And I'm picking 8 because the half-life is 8. Okay. So after 1 half-life, I'm down to half as much. After 2 half-lives, I'm down to half of that half. After 3 half-lives, I'm down to half of the half of the half. Right there. And then I'm down to here. And then I can be down to here. So I spread this one out a little bit more than the first graph we created. That's what that graph will look like. Okay. What's the mass remaining after 3 days? How did we get this answer? Well, we just put it into our calculator. Let's see, explain how we arrived at our answer. You could just go here and actually read it off the graph if you want, but if we have any equations, so why not use it? So what's the mass after 3 days? I'm just going to put that into this equation here. So 3 over 8 is my exponent. Pull out my graphing calculator. Just put it on the other screen. 250 times 5 raised to the power of 3 over 8. So my mass after 3 days is 190. Does it specify? Nope, doesn't really specify. Starts off with 3 sig, so I'm just going to leave it. So 193 grams. Okay, pretty good. Lindsay here bought a car for 15 years ago for a very specific amount of money. So that's probably going to be my A value. The car has tripled in value since that time. So in 15 years, my car's tripled value. So my p-value is going to be 15 here. It's a very strange amount here. So we're going to write an equation for this. So the value of the car after t years. So let's assume that time 0 is the 15 years ago. So she starts off with a car that's $1,200. And my base here, because it's tripling, my base is going to be 3. My period, or sorry, my time is going to be in t years, and my period is going to be 15. So that's what this equation will look like. We have that. So we're going to graph this. It's a growth function. So we can have a strange scale here. So what if I just said every tick here is 12,500? And this is going to be in years down here. Okay. So every 15 years is going to triple in value. So I don't know how I'm going to have that scale. Let's say, what am I looking for? After 40 years. So how many 15s is 40? So at least need 3 of those. One, let's say here. See, that's 15 years. I'm using the scale as my, or the period as part of my scale. Makes it a little bit easier to do the math. And then over here, so we have 45. Yeah, so that's a good scale. 15. Every 3 ticks is 15, so that makes every tick 5. So after 15 years, my car should triple in value. Okay, so let's say 1, 2, 3. So it should be right about here. After 15 more years, I should triple again. Okay, so at 3, so that should be a 9. Right about here. I'm not going to get to 45 because I botched my scale up here. So that's what the graph looks like. I'm not going to be able to see after 40 years. So what assumption we're making about this after 40 years is that it'll continue tripling every 15 years. It doesn't seem like that's very realistic, but we could just make that assumption here, make our math a little bit easier. So after 40 years, I just put a 40 in my exponent, and then I just punch in my calculator. Okay, I just have to find my mouse. Where's my mouse? There it is. Okay. And 40 over 15. So according to this, her car is going to be worth $243,000. That's probably not a very good approximation, but it doesn't really matter. Put too many zeros there. That's not good. Maybe $2 million for that car. That'd be nice. Okay. That's for this. I just wrote it up here. D, using a graph to approximate 50,000. So if I were to look at my graph here, 50,000 is 4 ticks up on this graph here. So this would be about 50,000 right here. According to this, I don't know, just a little bit less than 20, so maybe 19 years. So what I'm going to do is I'm just going to plug it into my calculator instead. And let's see what that looks like. So let's clear off what we have. So I know I want 50,000 in one of these spots. Let's create that flat line. And then I want 12,500 times 3 to the power of x over 15. Okay. Then we're in my window. Yeah, X max seems pretty good. This has got to be a little bit higher. So my Y max, how high the graph goes, has got to be at least 50,000 because that's where my line is. So let's put that at 60,000. There we go. So I want that point right there. So second trace number 5, intersect, enter, enter, enter. So about 18.9. So like I was approximately 19, like I said. So 18.9 years. Let me just put that on the bottom here. T is equal to 18.9 years. There you go. Looking pretty good. So here we've got a population of a town decreasing. I want to create an equation. P is equal to, I want to do a population P. After T years, it's decreasing by 2% per year. So that means my C value is going to be 1 minus, because I'm decreasing by 2% each year. So that means I'm going to have 0.88. So 88% each year. I got a current population, so I got an A value of 11,000. So my equation is going to be 11,568 times 0.88 raised to the power of, and it's decreasing per year. So that's going to be my period. So I just put a T there. Remember, T is the number of years. So put that on my scale down here. That's years. My population uses people, so I'm just going to leave that the way it is. And then this is what my equation looks like. Okay, it looks pretty good. I got 10 spaces here. I want to get to 11,000. I'm decreasing, so my max value up at the top here has got to be around this 11,000 number. Let's go 2, 4, 6, 8, 10, 12. That's not a very good spot to put that. I don't really have a very good scale here. Yeah, I'm just going to make it up. I'm not really too worried about this. We're going to graph we're just going to graph it in our calculator to figure out some of these other things, like use the graph to approximate population after 20 years, estimate, or use the equation to determine after 5 years. We could just do these both in our equation. So our graph's going to more or less look like this. This is my number up here. And that's going to decrease. I'm not too concerned about this. Okay, so we're going to state the transformation in our exponential function. So what transformations we have? So remember, our original exponential function just looks like this. See the x. The only thing we've done to this is just done a vertical stretch on our original transform graph here. So our original graph would have this. That's what our original graph would look like. So we've done just a vertical stretch on this graph so far. So we've done a vertical stretch by a factor of 11,568. So we're going to use our equation here to determine our population after 5 years. So I put a 5 there. I'm also just going to use my equation to do this one as well. I don't see why we're going to have to use the graph for this, because we have the equation for both of them. Okay, so I pull out my calculator. Just put it on the screen. It's not in the way. So 11,568 times 0.88 raised to the power of 5. Okay, so after 5 years, I should have 6,104. 4 people. I can't have 0.8 of a person. And then after 20 years, let me just quickly change the equation here. Have a little 20 there instead. I'm going to have 897 people. Okay, so the principal amount for this one here is A, so that's good, or sorry, 500, so that's my A value. It's invested per year at a 4.5% per year, but compounded semi-annually. So my period here is going to be a half, so every half a year, that's what that means. This is going to be my interest per year, so that's what that /A stands for. Write the exponential function for this. So we have V, we have T, so V is my investment. I have my initial amount, okay? It times it with my C value. Now, the thing is with my C value, it's going to be 1 plus the interest here. Well, because interest is per year, but it's compounded semi-annually, what I'm going to do with my interest, my 4.5%, is I'm going to have to divide it by 2 because of the semi-annual part. That's a semi-annually. Okay, so I go 4.5 divided by 2. Maybe change it into a decimal as well. Let's divide it by 100. Okay, so this actually is 2.25% for my I. So I'm going to add my I value here, 0.0225. I'm going to raise it to the power of t. I think t is my x-axis, t over 1/2. Okay. So 1.0225. And then because I'm dividing by 1/2 here, that's going to flip over to the top and become 2t. So here's my nice little equation for this investment. You can graph, it says graph the function. I know it's growing, so we can say that this is 500 right here. I can just go to my graph the same way we did the previous one, where here's my graph. About 500 times 1.0225 to the power of, and then I'm going to put x over, oh, sorry, no, x over. This should be 2x. Okay. I don't know what this part is yet, and then I'm going to go graph. Okay, so I'm going to have to change my x here a little bit so I can see more of the graph. Maybe my max here is a little bit off, so maybe I'll change that to be 2,000 instead. Let's see what that looks like. Actually, that doesn't look too bad. Keep that the way it is. And then, yeah, this doesn't seem too bad. What are we looking for anyway? We're looking for when the investment reaches $1,000. 15 years. So let's go 1,000 here. And they want to go to 15 years, so let's only go to 20. Yeah, it doesn't look too bad. Let's just make it a little bit bigger, make it more fun. So my Y max. Let's change that to 2,000 again. Let's graph that. Okay. So what I'm going to do now is I'm going to go to my table. I'm going to find some good points here to use. So my period every, yeah, so let's just go with, I don't know, I'm just going to pick some values here. Let's go 5, 10, 15, 20. So let's go up to 20 here. So 5, 10, 15, 20. Am I going to get to a good amount? Maybe I'll change where I started this value here. Because I'm not going to have too much here. 1, 2. So right here, I'm going to 500 right here. And then I have 1,000 up here. Okay. So at 5, I'm at 625. So right about here. At 10, 780 something, right about here. 15, 974 right here. And at 20, I'm beyond my graph right about up there somewhere. So this is what my graph looks like so far. It does have a slight curve to it, so it's going upwards. Looking pretty good. State the v-intercept. So my v-intercept is 500. This is just my initial investment. Okay, value after 15 years. I have it on my calculator already. You can just punch in your calculator. You can look at the table and find 15 years in the table of your graph that you created. Or you could just put in 15 into the spot up here, and you get $974.70. Okay, then we can use the graph to determine about 1,000. If I use the graph to determine about 1,000, slightly more than 15 years here, you can see that this was close to being 15. It says to the nearest, no, it doesn't say any nearest amount. So I'm going to go to my graph. Here's my graph. I'm going to put $1,000 on this. And then I'm going to hit graph. You can see there's a line. And then we go intersect. So 15.57, 15.6 years. Or 15 and a half, because we compound it every quarter, if I want to reach 1,000, 15.5 is not going to be enough for time-wise. You're going to see that. So I'm going to put down 16 years here. So I'm going to round it to the nearest half year because you're compounding every half a year. That's what semi-annual stands for. So I can't go 15.6. I got to either go 15.5 or 16 or 15. Now 15.5 is probably not going to be enough to get to your 1,000. So I could just double check that. So 2 times 15.5. So it's going to give me $996. So I had to go to at least 16 to make this work. So it's 16 years to get my investment to at least 1,000 or higher. I'm going to have more. That's awesome. That's just the way it's going to be. Cool. All right, so we have 2 more questions here. Student Council notices that the membership is growing by 3% per year. So it's growing by 3% per year. So that makes my C value 100% plus this 3%. We're starting off with a 350. What's my exponential equation? They're not giving me too much information about variables here. So let's just call M for membership. You could just say Y if you wanted to. 350. It is growing by this amount, so 1.03 raised to the power of, because it's per year, my period is 1. Let's say T over 1 if you wanted to. There's my equation. Use the equation to determine, get 560 members. I want to know when this is going to be equal to 560. Okay, so I'm going to plug that in my calculator. Go on. There you go. So we start off with 350 students. I'm increasing by 3% per year, and I'm going to put an X there. Awesome. And then I want to know when we get to 560. 560. Okay. I wonder if I could just graph that right now. Yeah, if I graph that right now, this is the previous scale from the previous graph. You can change that around until you get that intersection point. But I can see it here. 15.9. So 16 years, because it's per year, right? So I'm just going to go to the next year. So I get T is equal to 16 years till they get about 560. That's just using the graph. Okay. If you want to, you could sketch the graph here. I'm not going to bother sketching the graph here. I'm just going to use the graphing calculator that I have on my next screen. I'm on this side of the screen today. Let's put you over here. Okay. So Keegan here invests $1,000. That's my A value. With an interest of 3.75 per year compounded quarterly. Okay, so my period is going to be a quarter. What I'm going to have to do with my interest now is take that 3.75 and divide it by 4 to get how much interest per quarter. So 3.75 divided by 4. So I get 0.9374%. Okay, so that's going to be my I value. So when I create my equation for my investment, they seem to be using V's a lot here, so I'll just use the same thing. I'm going to go 1 plus my percent interest here, but I'm going to change it to decimal. So 0.009375, raised to the power of T over, because my period is a quarter, I'm going to put a little quarter there. So that's going to flip over and become this. So I'll just write out my equation. 1.009375. And this becomes 4T. So divide by a quarter, it just becomes 4T. There's 2 methods to solve this, and what they want you to do. the two methods solve this graphically. So you want to say down here, they want the investment to be 2,500. How long will that take? The two methods they're just talking about is that if you put the 2,500 on one side, you would just write it out here, just 1 second. You can leave it exactly the way this is and say this is y1 and this is y2 on either side of this equation, or you can make it equal to 0 and subtract over that number. Like this, and then graph this graph and just look for where does it cross the x-axis. And all you do is just graph the one side, then you look for our zeros rather than looking for an intersection point. I prefer the first one where I just graph the two sides and look for the intersection point. It's easier to find intersection points. Sometimes it's easier to see a zero rather than an intersection, but the math and the calculator is a little bit easier. So let's plug this into my calculator. Oops. Yeah. Okay. So this is I'm going to go 1 plus that answer there. Okay, so that's my C value. So what I'm going to do is I'm just going to store that into C so I don't have to type it out next time. So I'm going to go to my graph here. I'm going to start off with $1,000. I'm going to times it by my C to the power of 4x. All right, and then down here I'm going to go 2,500 is what I'm looking for this equation. And then hit graph. Okay, I'm not going to be able to see the 2,500 because I haven't changed the window. I want to go to 2,000 here. So I'm going to go up to 3,000 and hit graph on that. Let's see what it looks like. Not quite on the X there, so I'm just going to increase my X here to about 30, from 20 to 30. Yeah, it looks pretty good. Go second, trace 5, enter, enter, enter. And then about 24. What are we doing here? Quarterly. Yeah, 24.5 would be almost enough because 24.5 is not quite enough. So I'm going to have to go 24.75 because you can go up to the next quarter of a year. So what is it again? I'm sorry. Can't read that. 24.75. Oh, it says to the nearest year, so I might as well just go to the nearest year, 27. So about 25 years. So T is equal to 25 years. There you go. To be a little bit more accurate, to the next compounding, or the nearest compounding period, I would go 24.75 years. But because what they asked for here is the nearest year, this is what the answer they're looking for. There we go. Hopefully that answers a lot of questions. Hopefully I didn't bore you. Okay, and I'll see you in the next video. Bye.